So divide and conquer is one of the algorithm design strategies. So starting from this module, we'll see the different design strategies. We already saw a brute force to a certain extent among the algorithms we saw in module 1, like the bubble sort, insertion sort, and all those things can be considered as brute force strategy based algorithms. Okay? That means a common sense approach of doing things, a straightforward approach. So now we'll start kind of optimizing the strategy and trying to minimize the runtime or the time complexity. So the problem of divide and conquer is this. So given a problem of size n, so for example, what I mean by size is, say, the number of elements you have to work on a given problem. So for example, the sorting problem, you want to sort n integers, so n is the problem size. Okay. So in the divide and conquer strategy, what we'll do is we'll divide that problem for size n into sub-problems. Okay. Now how many sub-problems we divide, it's up to the strategy. So in this example figure I have shown here, I am dividing into 3 sub-problems, each of size n over 3. So the first sub-problem will consider only the first 1/3 of the elements, then the second sub-problem is to consider 1/3 of the next 1/3, and then the last 1/3. So you see here, according to this divide strategy, the sub-problems do not overlap. So the first 1/3 is different from the second 1/3 and the last 1/3, and so on. That's one approach of divide and conquer. The other approach is to divide the problem into overlapping sub-problems. So the first 1/3 overlaps with the second 1/3 here, then the third 1/3 and the fourth 1/3 of sub-problems. So that is another approach of divide and conquer. So what we are going to focus in this module, as well as the next module, binary search, is to consider problems where we are focusing this, not the sub-problems are not overlapping. Then in a later module called dynamic programming, we will consider a divide and conquer strategy where the sub-problems overlap like this. Okay. So again, by overlapping sub-problems, what I mean is, if you're working on an array, you assign the first 1/3 of the array to one sub-problem, and then the 1/3 portion I have shown here overlaps with the first 1/3 portion. So you consider some overlap between the sub-problems on the problems on the array that they are working on. So what is the time complexity of such divide and conquer strategy approach? Okay. So what we are doing is we are dividing a problem of size n into what you call b sub-problems, each of size n over b. So in general you can say n over b as a size of sub-problem. So in this case I am dividing the problem of size n into 3 sub-problems, each of size n over 3. So that b here is 3. So that's just the division part, how we are dividing the sub-problems. Now we need to solve the sub-problems. So we will say the time complexity of solving one sub-problem of size n over b is given as t of n over b. Now how many such sub-problems you are solving? Now in this case you could solve all the 3 sub-problems and then go about combine the solutions or sub-problems. But in general we will say we solve a of the sub-problems that we come up with. Okay. So each sub-problem takes t of n over b time to find the solution. So a times t of n over b will give you the time to find solutions across all the a sub-problems we have found. Now once we get the solutions of the sub-problems, we need to combine the solutions of the sub-problems, because each sub-problem will give you a solution only for that size, n over 3 elements, not for the entire problem of size n. So we need to combine, or what is called merge, the solutions of the sub-problems and find solution for the larger problem of size n. So what's the time complexity we encounter to combine the solutions of the sub-problems is given here as f of n. Okay, so that's the time complexity we'll assume to combine the solutions or sub-problems and arrive at the solution for the larger problem of size n. So here I have shown the time complexity expression. This is a recursion relation, recurrence relation for these two cases. So here we are dividing into three sub-problems, each of size n over 3. So I can say it is 3 times t of n over 3, the time to solve each sub-problem times the number of such sub-problems that we have to solve, plus the time to merge the solutions or sub-problems, which is f of n. So t of n, the overall time complexity to solve a sub-problem of size n, is 3 times t of n over 3 plus f of n. Now for this case, we have 4 sub-problems, each of size n over 3. So t of n is going to be t of n over 3, which is a time to compute solution for one sub-problem of size n over 3, and we have 4 such sub-problems. So it's going to be 4 times t of n over 3. And then the time to combine solutions of all these 4 sub-problems, which is f of n. So we can say t of n is 4 times t of n over 3 plus f of n. Okay. Any questions so far on the strategy of divide and conquer before we continue? Okay, so we'll see a lot of algorithms and strategies on this approach, so things will be getting very easy to understand as we proceed. Okay, so I said this f of n is a time to combine solutions or sub-problems. Now, if I give you a recurrence relation like this format, what approach you can use to solve such recurrence relations? In the first module, we saw one approach, which is like the substitution based approach, and based on reducing that in a linear format. Okay, the matrix, not matrix, the factorial multiplication problem. Now we are going to see another approach to solve recurrence relations, that is what's called the Master Theorem, to solve recurrence relations of this format: t of n equals a times t of n over b plus f of n. Now, in order to be able to apply this Master Theorem, this f of n should satisfy some properties. So f of n is a polynomial function, and it's also a monotonically increasing function. So what I mean by monotonically increasing is the function values should increase as n increases. So f of n is, say, n square. The values of the function increase as n increases. Such functions are to be monotonically increasing. So only if the function is a polynomial and monotonically increasing, that is f of n is polynomial and monotonically increasing, then we can apply this Master Theorem. So if you are not sure about what is a polynomial function, this is the definition of a polynomial function. So a polynomial is an expression containing variables and coefficients such that it involves only operations of addition, subtraction, multiplication, no division. And the exponents for the integers that are out there, or the variables out there, should be integers. So f of n is n cube plus 4n square minus 2n plus 1 is a polynomial, and it is of degree 3. So degree is the largest exponent within the polynomial. But we cannot say f of n equals n to the power negative 3 plus 1 is a polynomial, because what we have in the exponent is negative. So we cannot have a negative exponent as part of a polynomial. So f of n equals n to the negative 3 plus 1 is not a polynomial. Okay. So given a recurrence relation, you should be able to first decide whether that is f of n is a polynomial. If so, how to write the theta notation, or if theta is not possible, to write the big O notation. Okay, so any question before we do Master Theorem?